Hey everyone. I know it's been a while, but I'm gonna be back through the summer. Do as many videos as I can. I was hoping to have this out yesterday, but a little mishap with the audio in the last video, so I have to reshoot the entire video again. But I know that some of you would be glad to hear that I will be starting a new series. Um, Instead of lessons, I will continue with lessons, but I am going to start an adjacent series called What Is. So these What Is series is going to focus on a specific topic each time instead of like a broad topic. It's going to focus very narrow. And this time, I've got a lovely topic for you, one of my favorites. Brown Dwarf Stars. So, I know some of you have heard of these before, but before we actually get into the star itself, I am going to go over just a couple things. So, let's start with a definition. So, mass versus size. Size is self-explanatory. It's the physical, scalable, you know, thing of the object. If you have an object, you can measure it, that's its size. But mass is not physical, or it is physical. Mass is not about physical size. So you can have a large mass object that's very tiny physically. That would be like black holes, and in this case, brown dwarfs too. And I will get into that in a little bit. So the mass is usually weighed in kilograms. So when I talk about, when I say numbers of mass, it's going to be in kilograms. It will always be when I refer to them anyway. So I'd like to give an example because a lot of people know that brown dwarfs are close to Jupiter. So Jupiter's mass is about 1.9 times 10 to the 27th. That's kilograms. Mass is also what creates the attraction for gravity, and it's also critical for inertia and momentum. So that's just a little bit about the mass versus size, and that will help a little bit as we go through this. Now on to brown dwarf stars. This lovely image that you see right here is not a real image. It is a simulation image, I believe. It might just be an artist rendering. So an actual like person just took data and put it together and said this is what it would look like. So brown dwarfs are also referred to as failed stars. And that's one of the reasons why I like them, because they failed to us, but they're still working. And they occupy, if you look down at the bottom, these letters. So we have O, B, A, F, G, K, M. Brown dwarfs occupy M, L, Y, and T type. And as you can tell, only the M is on here. So that little bit down towards the bottom is one level of brown dwarfs. The other ones are not listed on the HR diagram because they are the furthest away from main sequence stars as we think of them. Even the supergiants and the white dwarfs, those are off main sequence, but they still were stars once. Going the wrong way with my mouse. So most of the brown dwarfs are substellar. So that's what they refer to them as. And why why have they failed? Is what a lot of people ask. Main sequence stars like our sun are able to fuse hydrogen 1 into helium. It's a process called proton-proton chain. So brown dwarfs, they can't do that. They don't have enough mass to take the initial hydrogen atom, which is very light, and fuse them together to make helium. And it takes four heliums, or four hydrogens to make one helium. But they can't do that, unfortunately for them. But they can instead fuse deuterium, which is the H2. It's two hydrogen atoms put together. They're a little bit heavier. And that process is why they tend to still glow. But they glow very dimly, and the fusion is very little, which is why they're so dim. But you do have a few that are 65 mass of Jupiter that can also fuse lithium. That means 65 times the mass of Jupiter. So we can actually relate brown dwarfs to Jupiter. This is why a lot of people have asked, is Jupiter a failed brown dwarf star? So essentially, is it a failed star? Well, the answer is no. I mean, it possibly could have been in the way back if it had gathered even more mass. Like, for instance, we see a lot of hot Jupiters. I would assume that they ate any other rocky planets that had started to form. And Jupiter, in its place in our solar system, is actually farther out than we've seen quite a few other Jupiter-sized planets. There's several reasons for this, but those ones probably ate the other planets, whereas our Jupiter was stabilized by several other things, like Saturn pulling on it from the other side, or Mars kind of getting in the way, the asteroid belt, stuff like that. So we're going to relate this to Jupiter. And Jupiter is a known size because it's in our neighborhood. And when things are large, we tend to relate them to Jupiter. Even stars, like brown dwarfs. But once you get past a low mass star, then we start relating it to the sun. Even low mass stars we compare to the sun, but they're quite a bit smaller. So, it's like 0.00. You get into small numbers instead of just adding a number to the mass of Jupiter. Okay, so this image right here is a good showing of what they are in size. I'm not sure if you can actually see it, but in the very end you have Earth. And so we know the size comparison from Earth to Jupiter and how much larger Jupiter is than our planet. But now we can compare the mass and size of Jupiter versus the brown dwarf. So if you look here, you can see that Jupiter is about the same size, and this is actually an average. So most brown dwarf stars are actually physically smaller than Jupiter, like their physical size. However, not that much smaller. It's about 15 to 20% smaller. So with our physical eye and such large objects, it's not something that we really can see with our naked eye. It's when you get into the different sizes from the brown dwarf to the low mass star that you see there, then it's obviously this one's bigger. But we can't really tell the size difference between a brown dwarf and Jupiter with our naked eye. However, the mass, from the smallest to the largest, can be anywhere between 13 to 80 times the mass of Jupiter. So they are physically quite small, but they are relatively massive. So if you were to take that number 13 to 80, then you can compare that to 1.898. Earlier I said 1.9, but the actual number is 1.898 times 10 to the 27th kilogram. Then you would get the mass of the brown dwarf star. So, as you can see, the low mass star, it's not on the screen, but right next to the low mass star is the sun, and it actually is just a little showing of it that touches the top and the bottom of the black. So that shows you the drastic difference between Jupiter to brown dwarf, which is very similar, then to a low mass star, then to our star. The colors we see of any star are within the visible spectrum. That's why we call it the visible spectrum. So humans perceive the visible spectrum as a rainbow, and everybody knows this. I mean, you've seen rainbows on sunny yet rainy days, and depending on the temperature, that's when you get the color of the star. Okay, so right here you can see the spectrum, the visible spectrum, and that lying on it is the main sequence, and then some stars that we know, like Betelgeuse is a red giant, and then white dwarfs down at the bottom. And as you can see on that image, the sun falls right in that yellow category. And I know a lot of people say, well, the sun actually isn't yellow, it's white, because when I take a picture or when I look at it, it's white. You should never look at the sun, okay? It will burn your retinas. You'll wind up with glasses worse than mine. So, in this visible spectrum, you see all of these different stars and their colors. And on the bottom, underneath what I had noted earlier with the types, underneath the types, you can see the temperature. So the sun is right by 6,000, which makes sense because it's actually about 5,800. But as you can see further down where the M is, it's a lot cooler. So it's less than 3,000 Kelvin. And because of that, it leaves them very deep, dark colors. So the image earlier seemed more like a brown, and that's why people say, oh, it's a brown dwarf, clearly, but they're not actually brown. So everybody knows what happens when you mix colors. You learn this stuff in primary school. The warmest of brown dwarfs appear to be orange or orange yellow, so just like a deep yellow orangey color. And that's because of the glow. They do glow still a little bit because of the deuterium fusing. But the coolest of them appear more magenta. For this next part, I really should have put an image of what the interior of the sun looks like, but I actually didn't feel like I needed to. As a basic level, everybody knows that the sun has layers. The fusion happens in the core. So they all have cores, but there's a lot more layers to the sun. However, with brown dwarfs, they are essentially just a full body convection layer. There's a core and there's convection, and that's basically it for them. There's no other, there's not the radiative zone and the corona. There's none of that in brown dwarf stars. So they lack the layers, and they're just not big enough, and that's what causes them to be, more like Jupiter in that sense. Where Jupiter, we from research that has been done, appears just to be more of a core and then just gases all the way out. So that's what keeps it from being, proper main sequence star. Those poor things, they just needed to be a little bit bigger, but if they were smaller, they would have been a planet. So they're somewhere in between, and that makes them just a little bit special. So since their brightness is so low, it took us a long time in our years, in discovery years, I guess. It took us a long time to actually find any evidence of them. It took about 30 years. So they were theorized in the mid 1960s, but we didn't find any until the mid 1990s. So yeah, that's about 30 years. And oh, excuse me, it's hurting my ear. However, we did find a binary brown dwarf system that is very close to us. So it's the third closest outside of Alpha Centauri and Barnard Star. And it's 6.5, or about 6.5 light years away. And those are called, I hope I'm pronouncing this guy's name right. If you know how to pronounce it properly, just phonetically put it in the chat. So there's Lumen 16A and Lumen 16B, and their masses are 35.4 and 29.4 Jupiter masses, and that's respectively. They orbit each other at a distance of 3.5 astronomical units. So Mars is 1.35, I believe, but Jupiter is 5.2. So, somewhere in between there. And their period of orbiting each other is about 26.6 years. So here I have a video I found from eso.org of them using several different satellites and different images to zoom into from where Earth is. As you can see, it's outside of, just to the left there was the, heading straight towards the center, but we're off center, and we're just going, as I said, 6.5 light years away. But you can see the comparison. All of these large, large stars, most of them are larger than the sun, since we can see them even more brightly. And you can really see the comparison as they get closer and closer, and you're still like, where are these binary stars that are brown dwarfs? Well, they're actually so tiny that the starlight from behind them, which is a lot farther away, is massive compared to them. So the zoom in actually shows you how small they are compared to other stars. But here you can see what they look like over time. So they actually appear to be, they call them the waltzing binary brown dwarf stars. And they do actually look to be dancing, and because they're so close, we can see their movement a lot better than stars that are a lot farther away, like the stars behind them. But as you can see, as they move, it actually will cover each other. So as when things are orbiting each other, they're both moving, and to us, it passes in front and it passes in front, and that's a transit. So when they compile them all together and then separate them, they actually look like this. Actually, it kind of looks like a W, but you can actually tell where they have transited in front of each other and where they are not. Sometimes there's two distinctive point sources, whereas other times there's not. There's only one. What's also very interesting about these two is that Lumen 16A is labeled on Caltech's archive as a brown dwarf star, as a star. But Lumen 16B on Caltech is listed as a planet, an exoplanet. Whereas on NASA, they're listed as binary dwarf brown dwarfs. I believe that's due to the fact that Lumen 16b exhibits weather-like cloud variations. Kind of makes it look more like Jupiter, just a glowing Jupiter. And it actually makes it one of the first brown dwarfs where atmospheric dynamics were observed. I can't From my research, I haven't seen any evidence of other ones exhibiting the same atmospheric dynamics, but it could just be the observations of them. We just haven't monitored them as well, or at least haven't published anything about them besides Lumen 16b. That will actually bring this to a close, but of course I won't leave you empty-handed. Let's look at this beautiful image that, as my seventh love, besides my kids and my husband and my dog, who's hiding somewhere over here, JWST. This image is a cluster of brown dwarfs, and as you can see from the glow and just the gases all around them, it's very hot in there. There are other stars all around, as you can see, and if you look pretty closely, you can probably point out all of the galaxies that are in the picture as well. Those are all pretty far away, but to our optical vision and the limits of even this awesome technology that we have, they kind of tend to look to be in the same plane. What a beautiful image, right? Well, I would like to leave you there. This was a great welcome back, and look forward to making more what is. If you have any suggestions on other what is, like I said at the beginning, very specific topics, just let me know in a comment. If you have me on Discord, you can add me on Discord. The Discord server that I operate for this channel, it's called Starship Purrseverence, because we are cats here. We are traveling through the cosmos in a Katship. I should have named it Katship. Okay, I'm gonna do that. Okay, so I'm renaming it Katship. This will be the Katship Purrseverence, and you can add yourself to that group through the link in the description. Also, if you'd like to donate to new equipment, new technology or softwares that might be needed to make this channel even better, the links are also in the description. But for now, like, subscribe, share, do everything you can to show people that you can learn about these things in a very simple manner. But for now, keep being curious.